Okay, so let's start with the current lecture on the peer-to-peer framework for social networks. So just what I wanted to say before, because there were some questions for that. So next week will be the time when you should hand in your first structure for the seminar papers. And first of all, for that, one point is I uploaded now some documents, some references for which kind of first entry papers you should have a look at. So for all of the, at least for most of the topics for which it made sense, I added 3 to 4 papers that you should have a look at. So that's now also online. And the question was what does it mean to give the um, structure of the paper? What is expected? Do we have to use LaTeX or not? So LaTeX is for this first step not required, so it will be also okay to have it in Word, but it should be a PDF that you upload. But I still would recommend for you to have it as a PDF, as a LaTeX. But just that there are some, yeah, not all of you are aware of how to use LaTeX, so there's a little bit more time to get used to it, but it will be required for the seminar paper later on. So what should be in the structure? So it is expected that you all have the questions, so what should be talked about in the seminar paper and what should be discussed, and that you have in mind or already prepared some kind of paper structure. That means what's the red line and what's the storyline, what kind of sections do you have, what do you want to talk about in each section, what do you want to present, and if you present for example, an overview on some specific solutions for one specific problem, then you would have a section on this solutions, and then you would have subsections on each individual solution, and you would add a reference to which paper you would cite and what you will talk about, so that it's somehow visible already from that structure document how the storyline in your paper will be. So of course not the whole paper is written yet, that's not expected, but at least the skeleton is prepared, that one can see what is inside, what's not inside, and I can think about whether something is missing or something is going into the wrong direction. Then I can already take some influence now and not on the final paper when everything is written and there's lots of effort in it, and I say that's not the right direction, go in the other one, there wouldn't be time. So this structure and skeleton should help to really, there you should present what you will write and about what kind of papers you will include, and there I can give you feedback on whether the direction is okay. Okay, yeah, that's expected for next week. Are there some further questions on that? So yeah, just what I said, what's later on required, that it will be all written in LaTeX and compiled, and if you don't have knowledge about now how to do it, how to write something in LaTeX, then there's still some time to do it, to pick it up from some tutorials. We cannot provide you that knowledge, so that's somehow I don't know, that there are several sources where to get this information from. That's not too difficult. Most of the students nowadays use it, and that should be doable. Okay, so today are there some questions on that, on the seminar? So if there are any questions anyway, just write me an email. I'm looking forward to answer them. Okay, so today what we will have a look at, so last time we had a look at how pastry is working and free pastry and a little bit on past. So the specific overlay that is used in a peer-to-peer framework nowadays, now we extend the view to something more general and look at more general peer-to-peer overlay issues, what can happen, what kind of problems occur, and what kind of solutions exist. And in order to do it, so first of all, I think last time we had a strong emphasis on pastry and how pastry works, but I want to more generalize it, because typically if you have one problem, that's not only occurring for one overlay, but it's more occurring for any kind of overlay in the same category. And the category for pastry is distributed hash tables. So what should they do? I'm not sure. Yeah, this is what they do. The next slide is basically how they should look like. So what they can do is that for every object, that has a identifier. One responsible node is found, and it is stored at that node. So you have this. You can publish a data item and a specific key, and you can retrieve it. And it's all distributed somewhere, distributed on the net, on the nodes. So you don't know really, as a user, where it is stored. That doesn't matter for you, but it's just important that the data is somehow distributed and you can access it. What kind of properties should it have? Of course, it should scale to millions of users. Reliability, the data should be always inside. And something is also said, so we'll have a look at this requirement, equal distribution of content among nodes. That's also somehow desired, but it's not really that every node should have the same amount of documents, because not all of the nodes are equal. So that should be taken into account. So how many documents does every node get? And of course, the network should somehow permanently adapt if nodes are going, leaving the network or joining. So that should be handled all the time. And there's also the problem that the responsibilities of the new nodes, so they get some new documents, the ones that left, they have to give the documents over. So there's always some dynamics. So this hash function, I'm not sure whether we really need the basics for it, what it does, just why is it a distributed hash table. So what it does, it maps a document or a number to a specific limited target domain. So the input domain is infinite, so you can put anything in this function, but the output, the target domain is limited. In our case, it's just this hash identifier of 160 bits. And what it does, so there you have this hash table, and it helps you to quickly look up the data and by the key that it had. And what it also gives you, if you make a question, I think it's basically probably too basics, but just if you have a hash table, then you can have a look inside whether it's there. If it's not there, then it's not there, and if you have a match, then it just says you have an entry under this key, and in most of the cases it's the something that you are looking for, and there was no collision. Okay. That's what they can be used for. So all general distributed hash tables are typically what they should do. So they are of fixed array size. That's also if you have it distributed. So pastry had 128 bits or 160 bits, and most of the overlays also have this bit size. And how they are called? Okay, hash buckets in general, but in our case they are all nodes. Insertion, deletions, that's more difficult if it's distributed, and to find it in a very quick time, basically. So the most main idea that you have to have is that you have this mapping, that you have one object on one node, and then this hash function makes the assignment, so to find really the node that's responsible for, to store it, and to look it up. Okay, so all summarized, everything's fine. So what do we have in distributed hash tables? So we distributed this centralized hash table basically over several nodes. We have them all distributed in the overlay network. They are somehow interconnected, that we know how to route. We have this routing, so in very general, and ID labeling, so that we in every overlay we have it, so that we really can in every overlay find the content that we are looking for. How this routing or ID labeling is done, that's different from overlay to overlay, but still the main functions are there. And what you also, if you want to use it, what we need is that we have to know the object's name. So if you are looking for some content, then you have to know already what the ID identifier for it is. That also implies some changes on your application. So you cannot just look for content that's interesting, but you have to have some data structures that gives you the information you are looking for. Object ID, this and that. So you somehow have to organize your search differently. So this is only some lookup. And also unique and known object names are assumed. So this is a little bit tricky. That is putting some requirements on your application. So you somehow have to manage the object names. So in the in the peer-to-peer social network, for example, the username was unique, and if you had a buddy with a specific username, then you could look up that username. Also, if you had um, an album of one specific user, then you had the username, you added a specific string, then you added the string photo album, and by using this string as an input from hash table, you got the object ID under which you found all photo albums, for example, of a user. So you really had some functions how to calculate the object names, and that's some limitation, but it's needed. Like, I mean, also in the internet, you need to know the URLs that you're looking up, and in order to get the website. So only since Google came up with the search, that was convenient, but before you had to know everything. Okay, so very generally, what all DHCs should then have. So now I want to go basically back from Pastry. Pastry is just one example, but in general, what they all have is this hash table that they are able to to have this responsibility for nodes to content. There you also need this mapping function. So which items do you map to which nodes? Because they are all in the same key space, but how do you make the matching? Then how do you have the routing tables? So how do you know what's the next best step towards a specific ID? And for example, in different overlays, you identify by the different metric what is closer, what is a better next hop. So for example, in Pastry, we had this prefix-based approach that with every step the prefix was longer and longer that was matching. In Chord and this some different overlays, there are different algorithms. And the next I want to present Chord. I looked up I'm not sure whether I presented it already. Did I present it before? Think I didn't. Who of you knows Chord? Okay, 5. Good. Because Chord is, if somebody wakes you up in the night and asks you what's the peer-to-peer overlay, then Chord will be typically the answer. Because Chord is the main known peer-to-peer overlay, I think. So in research it has more than 1,000 or 2,000 citations, so very prominent. And if there's a reference overlay that is somehow cited, then this one is the one. Because it's quite very simple, and still was one of the first one, and quite demonstrating all possibilities that you can do. So what does it do? So first of all, you have to know, okay, we have an identifier space. For that you have 160 bits, and we have a SHA-1 hash function that generates us this bits. So how do we get it? So the node ID we get from the IP addresses by just hashing it. Then we have the node ID, and the object ID we get by hashing the object name. So nowadays probably sometimes also the object itself, the content is hashed, but just to get the idea, so this is how you get the object ID. Okay, so how is then the topology looking like? So how do we connect the nodes? So Chord is organized in a ring. That means we have so the simplest topology is, this is every node ID is a number, and if you connect every node ID with the next one, so the next higher one and the next lower one, so that means a predecessor and successor in the ID ring, then you have a line, and then you connect the last one and the first one, and then you have a ring. So very simple. And for which objects is every node responsible for? It's responsible for every object between the predecessor node and itself. We will have an example for it. So that's basically the basis what you have. And in order to quicken up the routing, to make it a little bit better, you have this so-called fingers, which are pointing in the network. So you have O log n fingers, that means 160 fingers, that quicken your lookup time. We will see how it is generated. So this is a simple example with 10 nodes, and all of them have one node ID, and you also see below the node ID the responsibility range. So for example, the node 601 is responsible for Let's take a simpler example. This one, 3485, is responsible for its own ID and back to the predecessor node plus one. And you see all of the nodes are connected to the nodes with one higher node ID, and to the one with the lower node ID there are no nodes in between. So this is how the ring is created. So very simple from the idea. And here you can already do some routing. So if you are already interested in some specific object, for example with the ID 1000, then you could route around in the ring until you find it. Of course, this is very slow. It requires an average O log n. So there is some approach how to quicken it up, and for that you have these fingers, and the fingers mean that you have O log n fingers, and they point in exponentially increasing distances. That means you take your own ID, 709 in this case, and you add exponentially growing numbers, so plus 1, plus 2, plus 4, plus 8, plus 16, plus 32, and so on. And these are some IDs that are generated, and then you create a contact to the node responsible for that ID. So here, for example, it was added 256 or 512, and then you connect to the node responsible for the object ID 709 plus 512, and this is this node. So you also have a finger to that node. And by creating these shortcuts, basically, so these are node object IDs, and if you connect to the node IDs responsible for it, then you have shortcuts in the network, and that help you to reach every point in the network much quicker. Yes, so the goal lookup time will be O log n, so that means the maximum 160 hops, but typically it's only around 5 to 10. So how is it used? Oh no, it's not. First, how do we join the network? So how do we join the network? So if a new node comes in, what he does is he says, I just need any contact. So for example, the new peer 1289 knows that one, 3485. That's okay. Then I ask him to look up my ID. That means this node is responsible for my ID, so for this number. And then this is my contact person. Okay, so he will be my successor in the ring. And I place myself at my position. I create my successor link. I also get the information for my new responsibility range from him. I update the successor of my predecessor, so I contact him and tell him, okay, here is a new guy, so I'm now your successor, and I create the fingers. So this is how every node is just finding its position in the network, placing itself. It's like a distributed list, so just rearranging the successor and predecessor pointer and getting the information that you are responsible for. And how is then the routing done? So the routing, so that starts here. If you are looking for a specific object ID, then you just have a look at your finger. So you use that finger that is closest to it but doesn't go beyond. So if you are node 1000 and you're looking for item 3000, then the smallest finger, so the closest finger which doesn't go beyond, is then the one pointing to your own ID plus 1024, and this is the node responsible for, so this is your first hop, and that node also uses its fingers, so the next finger that doesn't go beyond but is closest is this one, so you come closer with every step, and the only exception is if you are the predecessor, if between you and your successor is the searched object ID, then you forward it to your successor. So this is the only case where you go beyond the number that you're looking for. And so within 3 hops in this case, you found the object. And the fingers are also nice because you have it in exponentially growing distances. With every hop, at least the distance to the goal ID is halved. So it's really decreased by the factor of 2. And that's why it's logarithmic, because in every step you halve the distance, and then you get quite quickly to the goal. So yeah, very fine. That's it. So that's chord. So this is basically a very simple approach how to organize the nodes in a ring, and how the routing is done, and how the responsibility ranges are done. And if you remember on Pastry, this is much easier, because in Pastry we had the leaf set, we had a bigger routing table, we also had this more complex routing table with the prefixes. So why isn't this the one used in the project group? So first of all, what is good? Okay, lookups will find the target if it exists. That's also the case in Pastry. It's also scalable as Pastry, O log n. It's also very popular, good. And there are many research extensions to it. So if people make some extension and they use some DHT to apply it on, then they use chord, because everybody knows chord. But the problem is, what you don't have is heterogeneity is not supported, so all nodes are treated equally. So although they are different, so they have to take the load that they get, so they cannot choose to take more, to take less. Also, that you only have unidirectional fingers. That means you only point your fingers in one direction, and the nodes pointed to are not interested in knowing you. That means half of the contacts that you have are not really interesting for you, and that's waste of traffic, and that could be improved. And also, the routing is only done one directionally. That means if you are looking for an object that's just some numbers behind you, you have to still go forward to come once across the ring and reach that object ID. So it really is inefficient in that sense. And Pastry is in that sense also better, because in Pastry you don't have this unidirectional routing, and you also know more. You are just quicker in finding in routing, because here you basically only half the distance. In Pastry, depending on how many characters you you have it. You at least divide the distance by 4 or by 16 with every step. So if you have a character set of 4 or 16. Okay, so but still chord is the most prominent one and should be known by everybody, because most of the examples really on what kind of problems exist in peer-to-peer networks and in distributed hash tables are focused on chord, but they also typically apply on Pastry. And one of the examples then I want to go into is how to treat the problem of heterogeneity. So what can be done to have nodes that are stronger also having more load, or what can be done to give them more load and to take the load away from very weak peers. And there I want to present two approaches. First, adaptive chord and Omicron. So as you see, typically the extensions are done with chord and not with Pastry, but they also apply to Pastry. So what is heterogeneous meaning? And I'm not sure whether this is relevant. So there are basically various categories of peer-to-peer overlays, but in structured overlays, it should not be DHT based, but more homogeneous. There are many overlays which are treating the nodes equally, so they all have to do the same, because typically this network research comes also from some theoretical aspect, and in theory that you have graphs, and in graphs all of the nodes are typically equal. And there's the other set of heterogeneous nodes where the nodes have different qualities, and this is really taken into account. Okay, so what can be done? So what's the motivation? So what we know from structured overlays and distributed hash tables is they provide us the lookup functionality. That's good, but what does it mean? Lookup functionality, that means that if you want to store some data, you find a responsible node and you put your data on it, or he's somehow taking the reference to the data. And typically all of the peers have the equal roles, so same routing table size, same storage space, same responsibility in the index space. That's all somehow probabilistically the same. But in reality, of course, peer capacities are different. So we have mobile nodes, we have servers. It would be nice to really set up some 5 or 10 servers that are very powerful, that that are, and this power is really used to support the data reliability, for example, or availability. So what are these heterogeneous overlays then? So they consider the differences in the nodes, they introduce different roles for stronger peers, and typically, so from history, super peers have been in this case. So previously you had Kazaa and this file sharing networks that had these super peers which were more powerful, had more tasks to do, and but we will see that's not typically the only way to go. So now I want to present adaptive heterogeneous code, so how that works. Again, so what was the problem? Only one directional lookups and all nodes are equal. And typically, so these request patterns are ZIP distributed. So I'm not sure who is aware of what ZIP is, but ZIP means basically, I'm not sure, is there a graph? No. But ZIP means that was some person and he identified that, for example, the usage of words in the English language are according to that distribution. So that basically means you have a factor, let's say 10, and then the most prominent word is used so with a percentage of 1/10, and the second one is used 1/10 times 1/10. So that means that you have a logarithmic. I will look up a graph for the next time, but just what you should know, it's easiest probably with the factor 2 to display. So the first prominent and most prominent item that you're looking that is in the network is, for example, filling half of the requests, and the second one is 1/4, and the third one is 1/8. So you always multiply the popularity with a specific factor, in this case with a half, and that you have very popular nodes and documents and whatever you are looking for, what you're requesting, and that's why you might have one single document that is very popular, and that's the problem, because you cannot go for having nodes having the same number of objects and assume that is load balanced, because that's not. So you might have one really tricky and very requested object, and this is generating lots of load. So the goal is basically that no node should be overloaded. So every node should define so what is the node load? When we want to talk about that no node should be overloaded, first of all, it can be defined by the ID range size. So that was previously in many literature done, so trying to have all nodes having the same size of responsibility. It can be also done by the number of objects one node is responsible for. There are also several solutions how to make all the nodes having the same equal number of objects responsible for. But the really realistic one is the traffic overhead for providing the objects. So if you want to have 1 million objects but nobody is looking for them, that's not a big load for you. But if you have one very popular object and half of the users are looking for it, then it's really generating lots of traffic, and that should be somehow made and distributed according to the node capacity. And what's the node capacity? That's the bandwidth that we are basically looking at, because storage space is, in our case with social networks, not the big problem. There you have profiles and whatever, but it's all small. So we are not talking about videos that you can download from the social network. So what is the goal? So the goal should be to have some balancing, and that means there should not be one node that is overloaded, and that's why it generates bad service. That means if somebody is looking for some content, then you want to have basically so if you are looking for some content, then you do not want to have it in a slow transmission, because other nodes are also looking for that object from the same peer. So what kind of goals could be there for load balancing? That all of them have the same load. That's not really realistic. There has been lots of literature and research on it, how you make all of the nodes having the same to do, but not considering the capacities. You could also give the load depending on how many load the nodes themselves generate. So if you have a very active node generating lots of traffic, then you also want him to have more load. That's also not what you're looking for, but you want something to have like that the node load is matched to the node capacity. So that's basically the goal. So the goal to minimize the number of overloaded peers so that only good service quality exists and that the transmissions are quick and fast. So if you have a very popular item, you want to put it on a very powerful peer. That's basically what is also desired in context of social networks. If you're a very popular person with very prominent pictures and all of the users want to download it, then you want to make sure that the data is not somehow overloading the hosting peer, and that's why only 2 or 3 users can download it and the rest is not having any results. Okay, so how can it be done? So let's compare what's the difference between Chord and ACORD. So first of all, what's the application? Let's have a typical file size of 1 to 10 megabytes, like probably also in P2P-based social networks. If you have an album with pictures zipped, for example, and stored somewhere in the network, and that you want to download or music files or any kind of documents in that area, so 1 to 0 megabytes, that's a valid approach. And they are zip distributed. That means that you have very popular nodes and lots of unpopular nodes. And how can you do then this matching of putting very popular documents on very powerful nodes? So again, this is original code. All of the nodes are equal. Most of the popular files are assigned by random, so just depending on which object ID you get, you find your position in the network in Chord. That's also the same in Pastry. And the node might be overloaded if it's too weak. And what is done in heterogeneous Chord, and this can be also applied in the PG, for example, for Pastry, is it's first of all hierarchical. That means there's a second layer, and like it's also here you have the one Chord layer, and here you have a second overlay, with every node in the Chord overlay also being part in the second overlay. We will see how it works. And in the second overlay, heterogeneity is considered, and that's the big goal, to have no peers overloaded. So what do we use the second overlay for? So first of all, you have a little modification to the Chord overlay. Instead of storing directly the objects that you can also think of in Pastry, you do not store the objects, but you are able to have some so-called mirrors. Then you would only store a reference to that mirror. So having a mirror, that means you can ask another node that you find fitting whether he wants to take your objects or your object. You are still responsible for that object, but if some lookup comes and asks you, hey, where's the object with that specific ID, and you are responsible for it, then you just forward it to the mirror node. So it means it's only one hop more, but you have picked the node which is capable to store the data. And so what do you use this second overlay for? This is a capacity overlay, and what it does is basically to help you to find suitable peers which have the capacity that you need. That means every node in this capacity overlay picks its ID based on its capacity. So if you have a very powerful peer, it has a very high ID. If you have a very weak peer, it has a very low ID. And with Chord, so here's a description how it is done, so that you basically have a maximum ID, maximum capacity, and all of the nodes find their position in the ID space. And with the Chord mechanism, it's already using, and it can be already used to sort the nodes like it's in this picture, with the very powerful at the highest number of the ID, and the very powerful, very weak one at the smaller part. And if you start to look up in this capacity overlay with some specific ID that you are looking for, then you find a peer which has that desired capacity. So if you think of a lookup in this capacity overlay as a lookup for a specific node with some specific capacity, that's what it is. So that's why the idea is, if you are overloaded in Chord and you cannot provide the content that you are responsible for in a given quality, then you start to look up in the capacity overlay, which also contains all of the nodes, and you find a node that is strong enough to carry the data, and then you ask him to become a mirror, you send him the file, and all of the following lookups that are looking for this file, you just forward on to that mirror, and you have served the lookup request like you were required in Chord, and you are not overloaded, and the load can be carried by strong peers. Here's some, this is the main idea, and of course there's some evaluation to show really that it's working. So the question was, so this is adaptive Chord, and this is the red one is Chord, and on the left side is the simulation of how many successful downloads were there in adaptive Chord, and I think there were 1,000 nodes, and file size between 0 and 10, and realistic bandwidth, and many lookups basically. And what came out? So first of all, if you have too many lookups, the success ratio goes down, and then the nodes identify, oh, I'm overloaded, so I create some mirrors, and I just use them as reference. Then you have a very high success ratio for your downloads as well. For the normal Chord, so we considered that if the download is shared so many times that you have a download speed below 1 kilobytes per second, then it's considered as failed, and this is in case of around 30% the case in Chord. So really lots of, around 8%. I'm not sure what this number means, but seems like 30%. Okay, so nevertheless, so in Chord you cannot serve with that. If you have this equal distribution of node IDs, of object IDs to node IDs, then you have overloaded peers and they cannot serve the content. And if you introduce this second type of overlay to find suitable capacities to serve it, and you use this additional mirroring idea, then you can really find capable nodes to serve your content, and that's still working on. And yes. Okay. This is the number of overloaded peers, and in Chord, I'm not sure why this is. That should be somehow in Chord. Out of 1,000 or 2,000 nodes, 6 at least, as you see, there are lots of nodes overloaded in the adaptive Chord. There are rarely some overloaded nodes. Of course, there might be some if you are very if you don't find capable peers, but then you also know that there are no further capable peers in the network that are able to take that load. So that's a simple modification just by introducing this one hop more and this mirroring and finding suitable peers to host the data. And with that, that's really a nice feature. And this can be also applied to Pastry, and this is more general than only here in Chord. What's also nice is that with the download duration is decreased, so and this time it was with normal Chord downloading these big files, and if the nodes have small bandwidth, then they are overloaded and it's all small, takes longer. But with adaptive Chord, it's quite quicker. And also, if you look at the download speed over time, so kilobytes per second, it's also quicker because you find more powerful peers that can distribute the data, and that's very nice. Okay, nice idea. So that means this introducing of the mirrors and having a capacity overlay to find suitable nodes helps to effectively use the different capacities in the network. It's also it doesn't require many modifications to call. So if you compare normal Chord to adaptive Chord, you still have this normal chord overlay inside. The only parts that have been exchanged is basically that you do not store the data yourself, but you might have a mirror where you position it on. So that means even if you would apply it to pesto, you wouldn't have to change in different parts of the code or of the protocol. So only the real storage would not be the data, but just a reference to the next hop where the mirror is. It's also very practically usable because data sizes are really realistic in online social networks. If you have a photo album, for example, and also the routing is only longer by one hop, so it's not really problematic. Drawbacks for quad. So still symmetrical routing is not given, security attacks, but that's at least the symmetrical routing is solved in PAS3. Okay, that was one idea how the different capacities of the nodes can be considered in the overlay. Another approach is Omicron. So it stands for Snaprovation. So it's of course one Greek letter, and it stands for Organized Maintenance, Indexing, Caching, and Routing for Overlay Networks. And it's also heterogeneous and also hierarchical. So you have different roles and you have different overlays that somehow work together. And the idea was, of course, the idea was to make a better overlay than any existing before. So this is not my slide, it was from the guy who made Omicron, but the idea was quite interesting. And we will see how this effective P2P overlay is created. And basically the main idea is that you introduce different roles that do different things, and that's why you can create more powerful overlays. So which goals were addressed? So first of all, I'm not sure. Okay, efficient mapping. So you want to have a locality. That means if you create your overlay network structure, you want that nodes that are connected are also geographically somehow close. That you have a efficient mapping. So that means some location-aware mapping, so that this contact, for example, takes less time than if you would contact two nodes in different continents. Then, of course, the contacts would take more time. What was also required? Heterogeneity, yes, to have different nodes with different abilities. Load balance, so they shouldn't be overloaded. And if the nodes go offline, then you do not want to restructure too much in your network. And of course, it should be scalable. So nice graphic, but it doesn't say too much. So how does it work? So first of all, I'm not sure whether this is, so I didn't introduce the de Bruijn networks. It's also not important how the de Bruijn network work in the end, but just it's important that it's one overlay and it has a nice feature that it's optimal with the diameter and the lookup times, and every of these nodes have a fixed node degree. So that's so you do not have too many contacts as a node, and you have a lookup time of O log n, so that's also guaranteed, and it's very nice. The only drawback of it is you need stable components. So as you see here, you have 8 nodes, and you cannot have 9. So you can have only exponential many. So 8, 16, 32, and that kind of. That means it's good from its properties, but it requires stable elements, and that you don't have typically. So how can it be done? It is done by introducing, by looking at one specific node, and this is not the one peer, but this is, let's say, 20 peers. And this is one nice idea because you still have the properties and the nice properties on the large scale, so on this network, but you also have these 20 nodes that you can organize more efficiently. And the question is now, what do you do with this 20 nodes? So in order to have, for example, this mapping, you only have to map a few of them. And the idea is that you have this kind of structure. So first of all, not all of the nodes do the same thing. So you have the author identified basically 4 roles that you need in a P2P overlay. First of all, maintaining the structure, so keeping up the contacts with other nodes in the network. This is the maintaining role basically. So it just makes sure that this node of 20 nodes is connected with the other nodes in the upper layer, so in the DPG network. Then you have the indexer. So this is basically storing the information which objects IDs you are responsible for and which objects you have. So here you need basically with the maintainers, you need nodes that are very long online, because then you have less updates between the higher level nodes. So if the maintainers are all the time online, that's very nice. Then you do not have to change your topology, and always the same time the same nodes communicate. The indexers have to have lots of storage space because they are storing the content, and they also should be long online, but it's also okay if they change in the meanwhile. Then you have the caching nodes. They are basically the ones that are uploading the data. So if somebody asks for some content, this is basically the backup, and this is the main contributor. So if they have storage bandwidth, then the caches are used. So here you can have 20, 30, doesn't matter. And then you have the routers, which is basically if you are looking for some content, then you contact them to find the content for you. So you have different roles that you somehow organize in this set of 20, 30 nodes, and they all have their capabilities, and according to their capabilities you give them a specific role, what they should do. And in total you see that the capacities of the nodes are used, and it's helping to make the overlay better. So here, for example, if you do some lookup, that's more how the P2P network works like, but you start the lookup at one node, he contacts the routing nodes of the other cluster basically, and once it is in the cluster, then it's processed. Typically it should be processed by the caching node, because that should take the load from the indexer. So just, I mean, you can extend your imagination and just think of other types of roles that are useful and how to combine them. But the main statement here is that you can have different roles in the network, and by introducing this type of clusters, you can also make use of the different capacities of the nodes. Okay, so one question the authors asked themselves, of course, is it better? And here you see also they also compared their solution with Chord, and of course it was better than Chord. So they used an average cluster size of 8 and with an out degree of 4, and it was better at the end. And it was also theoretically modelable. So it's very supported by theory and simulation. It's quite good working. And one of the main questions was how do you pick the peers based on the capacities? So previously we had it in Core that the nodes picked their own position in the network by their capacity. Here they thought of, okay, the one important aspect is how long stays the node online, and how long will it stay also in the future online. If I expect that he will stay online for the next weeks instead of just 1 minute, I will give him a role according to that. And the idea was, okay, let's have a look at so this is how the peer lookup the peer lifetime is distributed, and there are different so the black one is based on measurements. There are different distributions trying to match it, and the statement is basically that the probability is very high that it's only living for a very short time, and the probability that it lives for a very long time is very small. So this is basically the statement. So there are very many nodes who go offline after a few seconds, after a few minutes, and only a few nodes stay online for a long time. So the idea was this so-called burn-in method. I'm not sure whether there's a graph. No. The idea is to identify reliable peers and to make this not too many times. The idea is to look how long the nodes have been already online, and if they are already online for a long time, then it's also more probable that they will stay online for a long time. That means if they didn't fail in the first minutes, then they will stay online longer. And if they have been online for 1 week, then it's more probable that they also will be online for the next week. And that's the burn-in method. That means previously this light bulbs have been tested like this. They were switched on for an hour, and if they didn't burn, then they were sold, because it's more likely that they will not burn at the customer's place. Okay. So what is this statement? So I think that's not too important for us. Just they mix the lifetime of the nodes to have a more matching distribution. Okay. So yeah, that's the burn-in method that I described. So if you know the lifetime and the lifetime distribution, then you can really test how long has he been living, and this is the hazard rate. That means what's the probability that the object or the node will go offline. And if he already survived a specific time, then it's better. No, then the node can be considered as somehow being over the top, and he's reliable, and that node can be taken as reliable. Okay, so that's the statement. Basically, if you want to find long-living nodes, then you should have a look on how long they've been online, and the longer they've been online, the better. Okay, that's it for Omicron. Basically, these two overlays just said it's very important also in social networks and P2P-based social networks to make sure that no node is overloaded, and that if you have some content stored in the network, then the content should be somehow matched to peers that are capable to store it. This is not the case nowadays, because also in a current social network P2P framework, there's just FreePass and FreePass doesn't do it. So in FreePass it's just randomly assigned who's responsible for it, and that node gets overloaded. It might be replicated, but it's the nodes might get overloaded. And it's also not clear how the replication takes effect. So if you have replicated 10 times, whether that's somehow better if you have a high load object that people look for. I don't know. But it needs to be solved, so that's why it's good to know how it can be done. Next, we will have a look at other optimization of structured peer-to-peer systems. So we'll have a look at what can else be done to make the overlay better. So in here as well, it's not necessarily related to Chord or any overlay, so it's very general. It can be also applied to pastry, and we will see what kind of problems occur and what kind of solutions there exist. So first of all, again, this is more a solution, and what's the problem? Again, the popularity of objects, and what I talked about just recently, so with the replications. So we know the popularity of queries and documents in the network is not uniform, so there are more popular people, or let's say more popular pictures than other pictures, or whatever information that you look for. The people are just attracted to more popular stuff, and that's generating more load, and that's why you somehow need to distribute the load. And one approach could be caching. And what is caching? That means to have a copy of the document, and you also, once you downloaded the document, you also share it with the others. So if somebody else is coming and wants to have the article, probably you will serve him, and not the main responsible node. So every intermediate peer that have received some information that might be useful for that query might help as well. And okay, tip that we already had, how the distribution is. So how can structured overlay networks take advantage of it? So what can they do? Something that they can do again, it's the example with chord. So typically you just have the normal routing, so you use your fingers to come closer to the responsible node, and then the answer is given by the responsible node. What can be done if you would have some caching nodes is, in this case, you could have caching two different ways. Either you already know the content and can send it back, because probably that caching node was also once looking up the content and it already has a copy of it, so you can send it back. Or you can, of course, send a shortcut back so that you do not have this multiple hops. So what you can do is you either modify the routing procedure that you do not go over your fingers, but you know already the answer where the lookup ends, so you can answer that back. Or you can also send back the content itself. So two approaches how it can be done. Of course, so does it scale? Because if you start the queries, then you have only limited cache size. So what can be done? What is this? No. Okay, so you have a limited cache size, so that means it doesn't take too much effort to do so, to use a cache. It can be incrementally deployed. That means you do not have to change all of the nodes to support caching to have a benefit. So if you have only 10% of the nodes having this cache, that also helps to improve the overall performance of the network. So this original and enhanced peers can coexist, and that's a benefit, because sometimes if you have really already a network with 1,000 or 10,000 nodes and you would like to improve it with caching, then you cannot ask them all to change their software, but you can ask the new nodes to use caching, and then that helps already. And what's somehow still a problem is that the copy that you have might get old. So how do you make sure that you have always the newest version? And typically what is done, or what can be done, is if the node goes offline, then also the caches go offline, and that makes sure that the next time a fresher version of the document or article is retrieved. But still, you see, this is not optimal, because you might still have outdated content that is in the caches because the nodes don't go offline. So that's not quite clear how to solve it. How does a cache look like? Basically what there stands, so what it is a cache for, when it will expire, so when you will delete it, how frequently it has been used, pending queries and marked. Okay, it's more important for the cache operations, these further entries, because you can also, if you have only, let's say, 10 entries for your cache and you have to decide which of the entries you keep, you can go for different strategies. For example, you can replace, so there are different, you can have a first in, first out, or last in, first out, or least recently used, or least frequently used. And it's very simple basically. So either you replace a cache entry, you can put one inside, or you can take one out. So it's not very complex, and it still helps in improving the network. And what it shows, typically, yes, it works. So again, with chord, what has been tested with different expiration timeouts, so how long the cache stays in the network. And experiment A just says, I have, so let's say with experiment B, so if I have a cache size of 300 and I reset my frequency counter every 10 seconds, so at least the bigger my cache, the better, and the more, the longer I keep them in the cache, the more cost do I take over from chord. So this is the saving, no, the percentage of routing communication costs. So in comparison to original chord, here you only need 50% of the traffic, because the rest is handled by the cache. So it helps in some way, and it also takes away the load from the responsible nodes. Okay. So what is it good for? It reduces also routing cost, because you don't have to route so many hops. You do not have to go to the responsible node. It can be incrementally deployed, so it's also good when 10 or 20% of the nodes use it. No additional overlay is used. Simple design, so it's very simple to implement, but the drawback is this consistency problem in case of update or delete. So if somebody changes the article, then all of the caches are invalid, but they don't know it. So you still serve the wrong content for a long time. And that's also the problem. So if you have a very long serving, so this expiration time, so if the expiration time is high, that means you keep it very long in the cache, then you have the most of the benefit, but you also have for a long time this inconsistency. So different versions of the article are replied. And also you need, okay, more additional storage space on other nodes, that's okay to do. Okay, so still results, you can save up to 50%, and the overloaded nodes are somehow less overloaded because it's more shared, and the more popular the content is, the more caches will keep that popular content, and the less load the responsible nodes will have. So it somehow also helps. Okay, another point that is also often discussed in how to improve P2P overlays in general, so what should be done, is so-called underlay aware P2P topologies. That means, so what is the goal? So the goal is that we have, this is the application, okay, like the social network, we have some requesting content, we have some overlay, but we also have the network itself, so the internet. And this internet keeps lots of information like where the node is located, what bandwidth it has, what latency, delay between two nodes, jitter, that means how the variance in the delay is basically, then we also have loss and geolocation and network translation issues. So in this underlay there's lots of information hidden, and it might be useful to know what's under there, to have this information to make a better overlay. So this is basically the idea, to take the underlay information from either you measure yourself, end host measurement, either you have the internet service provider like Telecom or Vodafone or whoever who tells you what you have, for example bandwidth, and or other kind of measurements, but that you have at least more information about the underlay that you can make use of to create better overlays. So what can be done? Okay, so this is the introduction. So what's the underlay? That's basically all below, and this is the whole internet that we look at. So the physical medium access control and network and transport layers, and there are different affecting partners that take effect basically on the performance of that network. So the ISP location, that means whether you're at Telecom or at Vodafone, whether you're in Germany or you are somewhere else. The latency, the peer resources, that all come into play for that network capabilities that you have. You have different approaches to get information. Yeah, let's just assume we have that information. What can we do with it? So first of all, you can make your peer-to-peer overlay ISP aware. So ISP, that's the internet service provider, and to make it ISP location aware, that means that you prioritize, for example, nodes from the same internet service provider. So if you are with Deutsche Telekom, then you would try to connect to more nodes from Deutsche Telekom and to share data with them, because that would also reduce that would keep the traffic that you generate in the in the Deutsche Telekom network, and that means that for the Deutsche Telekom it's better, they don't have to pay so much to the other ISPs for this inter-ISP cost. So typically if Deutsche Telekom would send lots of traffic to Vodafone, they have to pay them. So, and that's why the internet service providers would be very interested if you would keep your traffic in their network as much as you can, and in order to minimize this inter-ISP traffic. What you can also do is to try to make your overlay latency aware. That means, what is latency? That's the delay between two nodes. That means if you send a message to, if I send a message to one of you, then it takes, for example, 200 milliseconds. And if you would be on the other side of the world, that would be 600 milliseconds. And if you have in your overlay connection, your topology, more neighbors that are latency closer from the latency, then you would improve the overall overlay performance, basically. So if every node would still maintain, for example, in chord all these fingers, or on pastry all these routing contacts, but try to find better connections based on the latency, then you still have the same hop count, but every hop takes less time. So that would be very nice. What you can also do is to have it geolocation aware. Yeah, that means that you try to connect to other German nodes or other European nodes to allow for location-based services. That means sometimes you would like to send a message to all German users in the social network, for example, and then it's easier if you have the topology already geolocation aware, then you can make these kind of messages more easier. So then you can have a location-based broadcast, for example, that's only considering the users in Paderborn. That's, if your topology supports it, then it's quite good. And what you could also do is to make it peer resource aware, so to pick your network contacts based on the capabilities of those nodes to create, like we saw in before, for example, you could create a nice mixture of nodes, so some that have lots of bandwidth, some that have lots of storage space or CPU power, so that they build, for example, so clusters that you can use for any kind of purpose. So these are the four aspects of underlay awareness that you can optimize your overlay for, and optimize your pastry and your contact selection for. And this is generally applicable, so it doesn't require to have a new overlay that you can also apply in pastry. For example, in pastry we had this routing table, and it was only needed that the nodes in the routing table match a specific prefix, but nothing more. So if you have a set of 5 nodes fitting into that match, then you can pick one according to its latency or according to ISP awareness or whatever, in order to improve your overall overlay performance. So why is that all? How does it all work? So first of all, I think that's just a longer description. What you should just know for this ISP location awareness, typically the internet structure looks like this. You have the customers, they are connected to Deutsche Telekom. Deutsche Telekom is connected to some German ISP, some bigger one that you don't know, and they are all like this. And typically sometimes they have some agreements. They have some agreements on when they have to pay each other, and in any case it's best for the IPs if just the traffic stays inside. And for example, if you are that node in the middle and you could be served by this node or that node, then it would be better if you are served by one in the same ISP. That just improves. And this is, for example, how the matching can be done. What you should just keep in mind, if you have large data transfers and you can be served, for example, in the same ISP, then you should try to do so. And if you cannot be served, then you should try to find somebody else outside. This was this kind of topic was very popular, let's say 3 years ago. I'm not sure whether the peers and the nodes really benefit of it. In this case, only the ISPs benefit, I see that, but I'm not sure how the users benefit. Because if, for example, you find a better match outside and he's faster uploading to you, then why should you take one of your ISP contacts? I'm not sure. But this is also interesting. Latency aware. What does it? Like I said, it's the idea that you pick your neighbors based on how close they are to you. And typically you cannot know if you have 10,000, 100,000 nodes, then you do not know the latency to all of them. That means, how do you estimate the latency between two peers? They are basically, this one practical approach. It's called landmark-based prediction methods. And what people have done is that you have, let's say, this landmark nodes 1 to 5, and there were 100, but not more. And if you ping all of them, and if you define your latency to all of them, then you can somehow identify in a multidimensional space your distance and your coordinates. So just think of a two-dimensional landscape, like in this case, and if you ping all of them, then you get a distance. So in this case, it's long as this, and if you ping to that, it's long as that. And there are not so many positions in the two-dimensional map where your position could be to have that distances. So after doing some triangulation, like in GPS, you find your coordinates in this multidimensional map that somehow fits to the measurements that you did. And by every node knowing its coordinates in that latency map, they can communicate these coordinates, and then also two nodes can see, okay, this is my coordinate in the latency map, this is his coordinate, so we would have approximately this and that latency. So you can, although you didn't do any measurements with each other, you can somehow estimate how much it would be, because you know how much it would, your latencies to the reference points. And by using this information, you can create better topologies that, like I said, if you have better contacts but with the same property like in previous routing tables, you have the same number of hops but they are quicker. Oh, that's it for the underlay awareness. I think that's because the other ones, geolocation awareness, that's rarely used. I mean, it's a nice idea, but it's really hard to make a routing example. And peer resource aware that we already discussed before. Okay, so what do we have else as an issue? And those of you who have been in the lecture peer-to-peer networks, they already know this topic. And net traversal is really an issue for peer-to-peer networks. So what is net traversal and why is it a problem that we have? So first of all, if we consider that we have, let's say, 10,000 nodes in the network, and it's peer-to-peer based, then they should be able to contact each other. So that's very basic, but it's not so trivial, because most of the nodes at home, they have some kind of NAT box or firewall. Because you have this, what do you have at home? I don't know, so this DSL routers, and the DSL router has one outgoing, so it has one outgoing public IP address, so it can connect anybody. But internally, at home, you might have different devices. So you might have 2 notebooks, 1 desktop PC, whatever, and they have internal IP addresses. And if some request comes to your DSL router at home, then it doesn't know to which internal device it should be forwarded. So because typically you have this situation, and if you do not specify ports that are, for example, I am at home, I have a specific port that links to my notebook at home, I have one port that links to my printer, so I can access it from outside, but I have to know these ports and I have to make them manually, I have to install, I have to specify them, and typically if you do not specify anything, then only these out connections are enabled, and the in connections are difficult. And how does this net traversal work? I'm not sure. Yeah, there will be a slide most probably, but typically if you connect to the outside world, then your net also memorizes basically the destination node and destination IP and port address, and it has the connection when the answer comes from which node it was coming from. So that's how net works. And typically in 60 to 80% of the peers in the peer-to-peer overlay are hidden, so they are not really contactable. And this is really a big number, so this must be reduced. And Pastry is not having a solution for that, so that's why it should also be addressed. Okay, yeah, from outside you cannot be connected. Good. Okay. So how does it work? like I said, so typically you have at home, so this is basically the peers that you have at home, the nodes. And yeah, why do we have network address translation? Simple solution, because we don't have any IP address, not enough IP addresses to serve every device. So that's why we only have one out and public IP address, and internally we have this private IP range, and that we can use. So how does it work? So internally, this is your IP address, for example 192.168.1.1, and the port, and that's the node that you want to contact. And you send it via your DSL router with the net inside, and this is the public IP address of you. So it rewrites it, because otherwise in the internet it wouldn't be readable. And this is the public port from which it is sent. So it is rewritten in the IP header. And when the answer comes, it's also using this public information that it received. And that's why by using the public IP address, the answer also gets to the right point. And by knowing, okay, this was the sending port that I sent from, I had internally in the net the matching. I have to send it to this one, to this node. So basically here you have also a hash table, and by memorizing what was your input, you know to which port peer you have to pass on the message. So this is how it works. And of course, if somebody else contacts you with some specific port, then you don't know as a NAT to which of the several peers or nodes that you have behind in the private zone you should forward it, because there might be here you might have 10 PCs, and you get a message with a specific port that you never saw before. You don't know which one is to be passed to. Okay, so what can be done? So there are different approaches how to solve this NAT traversal for P2P networks. We will have a look at a few one. So first of all, what you can do, of course, you can have port forwarding to have static mappings in the NAT device, that you write down if a message comes for this port, forward it on to that device. You might have universal plug and play, that we don't have a look at how this works. Basically just if you send out a message, it memorizes where it came from, and that you can automatically configure your NAT with that. What can be also done? Oh, it's good, I have pictures for it. So what can be also done? This is basically I'm not sure. Yeah, what can be done? Okay, so this connection reversal, that's an approach. If you identify that you cannot contact somebody, then you try to send via any other way a message to him so that he contacts you. So that's, for example, if you cannot contact some node in the chord overlay directly, you can send him via the chord lookup a message to tell him, I cannot contact you, contact me, and you might be contactable. Also, you could do some relaying. So in this case, node A wants to contact node B, but it cannot. So that's why it asks this server or this node, which is public, which doesn't have NAT, to connect B. I don't see how this works. But so, okay. I'm not sure why this should work. I think this was just what I said, so it shouldn't be no, I don't know why this works. So just ignore this picture. But typically, if this relaying happens, what you have is that you have some public node where you store your information, whom you want to contact, and this public node should be contacted by the one that you wanted to ask something. So you need some point where you can exchange messages and it's not blocked. And what can also be done is hole punching, that we will have a look at how this looks like. Okay, this is more. So about the relaying. So what does it mean? Yeah, like I said, they just contact the node, some node that they both can contact, and that they are able to communicate with and store the information there. But more important and somehow also challenging is the hole punching. So the idea is that you try to, with the help of some public node, you try to establish a connection between these two. So here you see the private IP addresses, here you see the public IP addresses, and this is the public node that you can contact. And what you want to do is to have a connection between both, but they cannot communicate with each other because they don't know the internal addresses and they don't have this mapping enabled. So what they do is, first of all, A sends a message to the server, I would like to communicate with B. Okay. So what the server does is it should know the internals of B, because both of them should have registered once, to tell what the internals are, and server S tells the internal contact of B. Yeah. In the next, client A tries to establish the connection to B, but of course it is blocked. But so here you see it just contacted B with the public endpoint, and as this net doesn't have any mapping to the internal nodes, it's dropped. But the good thing is that A has now a hole in its nut, and it knows, okay, because now the nut is expecting an answer, and then it would know where to pass it on. So now here we have a hole. That's good. Second, somehow B needs to be informed that there is A who wants to contact with him. That's why they should always sometimes communicate with this central server or central node to ask whether some connection interested nodes are available. And in this case, B would notice, oh, there's somebody interested in me, and then I would also try to contact him, and because he already contacted me, it's possible. So that's basically the idea, that you create the hole in your net by having an unsuccessful attempt to connect, but with that unsuccessful attempt you open your hole in the net and you can be contacted. So now the question is just how to communicate over the server that you want to be contacted, but this is just a protocol issue. And then you can communicate directly. Okay. So some little issues. Of course, these UDP net holes are closed after a specific lifetime, so you need to always send some messages. With TCP, it's even more difficult because there you have to have this handshake protocol, but it at least works, but it still has the limitation. It's not working for all the net types equally, because there are different net vendors, different producers of such routers. There are different net types. There are different behaviors to this unsuccessful attempt to open the connection. So sometimes the net hole is only opened if there was a valid reply. So sometimes it's difficult to solve it. So that's also, so it's required to have two nodes communicating with each other, but it's challenging to do so. Yeah, that's it for today. I think we are also good in time. So for the next week, as it was said, and it's also on the website, so what I would like to have is this structure of your document. So how will you write the papers, which elements you will discuss about, what kind of papers you will consider, and what is the red line, what is the storyline. And yeah, that's it. So if you have any questions, write me an email or ask me then directly. So thank you very much for your attention.